Uh, Good afternoon to all. Welcome to the 10th week tutorial session of NPTEL course Convective Heat Transfer. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. And in this week, we will see a few a theoretical problem based on the turbulence. So basically, the lectures that were covered in this week are based on Reynolds average Navier-Stokes equation and their closure, how to close it using particular models, then boundary layer in turbulence, how the energy will be passed on from the large scale entities to the small scale entities, and through the cascading effect that was discussed in the boundary layer energy transfer, heat transfer in the boundary layer. Without wasting much time, we can move to the problems. Look into this question. It's a derivation. So we need to prove the validity of the time averaging rules of the following equations. So these were the set of equations that we have actually seen in the lectures. So we need to prove that this is right. The first equation is u direction plus v direction total velocity average is equivalent to the u average plus v average. Then the u mean component multiplied by the variable component is the time varying component, fluctuating component of the velocity. That product, the total average will be equal to 0. And then the product average of the velocity will be equal to third equation. The product average of the velocity will be equal to the sum of the product of the sum of the first term will be the product of the mean terms, and the second term will be the mean of the fluctuating terms, and then another 4 set of rules. So we need to prove that the following equations, the time averaging rules are valid. Basically mathematics in this case. Look into the problem. I'll give you a couple of minutes to look in, and I'll also try to solve it afterwards. Okay, then we can try to solve the problem. Am I audible? So in this case, we need to prove these rules are valid. So before that, we will write what does these terms mean. So the definition of U bar is equal to 1 by integral 0 to T0 U dt, that is time. You average the time. You average the velocity over time and divided by the total time. So T0 minus 0 T0. So that is U bar. And U dash bar, similar to that, that will be equal to 1 by T0 0 to T0 U dash dt, where U is equal to U bar plus U dash. Similarly, V will be equal to V bar plus V dash. So the first equation says, the first equation says U plus V bar is equal to U bar plus V bar. So using the definition of averaging, so U plus V bar will be equal to 1 by T0. We can denote it by A and you can denote it by B. So, instead of U, put U plus V. We can write it as 0 to T0 U plus V dt. That will be equal to 1 by T0 0 to T0 U dt plus 1 by T0 0 to T0 V dt. So this is same, and this is nothing but U bar, and this is nothing but V bar. So the first equation is proved. So basically, basically this is more like a distributive property. That is, U plus V, the whole bar will be distributed. That bar will be distributed to their individual units. So we'll move to the second part. We have to show U into U bar into U dash, the whole average will be equal to 0. So the second term is U bar into U dash, the whole average. We have to prove it is equal to 0. So using the definition of time averaging, so that will be 0 to T0 U bar U dash. Beg your pardon, this is U bar. u bar into u dash. So that will be equal to u bar u dash dt. So this u bar is a mean term. So you can take it out. That's a constant. That is a time independent property. So you take it out. So u bar divided by T0 0 to T0 u dash dt. So this will give to the second identity that we have, second rule that was present. So that is the time averaging of the fluctuating term will be equal to 0. This will be equal to 0. Because this term is equal to 0. So that's also second part. Now coming to the third identity, that is UV bar. So multiplication of UV and the average of that one, that will be equal to same using the identity of the time averaging UV dt, that will be equal to 1 by t 0 to t0 u plus u0 u plus u dash u bar plus u dash v bar plus v dash dt. So that will be equal to 1 by t using the multiplicative rule. So we distribute we multiply the first term and the second term, so that will give u v dash plus u bar v dash plus u dash v bar plus u dash v dash and the whole dt. And taking the individual terms, this is a constant, so u bar v bar 1 by t0 dt plus the second term will be u bar, you can take it out, divided by t0 to t0 v dash dt. In the third term, we can take out v bar 0 to t0 u bar dt plus 0 to t0 t t0 u dash v dash dt. So as you could see, the second term will be equal to 0. The third term will be equal to 0 because the time averaging of the fluctuation term is equal to 0. And this integral will be equal to 1. So we get u bar v bar plus 1 by t0 integral of 0 to t u dash v dash dt. So this is the averaging. This will be basically the averaging of u dash into v dash. That will be u bar v bar plus u dash v dash average. So that completes the third identity. Now we can move to the fourth one. Fourth one says u squared is equal to distributes it among the mean and the fluctuating terms, just similar to this case. So it will be u squared average will be equal to basically in the case of the in the u previous case is we have seen the product of u and v. When the second v becomes equal to u, we substitute that straight away. We can use the third identity and we can deduce the fourth identity from the third one. So when so we need to number the identities before that. This will be equation 1, equation 2, equation 3, equation 4. It's basically u into u bar from equation 3. U bar will be equal to U bar squared. Basically, U bar into V bar equal to same U bar square, and U dash squared the average. So that solves the fourth equation. Now the fifth one, it's a you have to calculate the different derivative of this velocity term. So that will be basically dou u by dou x. The dou u by dou x average will be same as that of dou u average by dou x. So the reason why we do this distribution of these identities is because we will these are very useful while deriving the Reynolds average Navier-Stokes equation. So we just need to plug in these identities straight away, and we can get the results immediately, rather than going at that particular, rather than deriving everything at that particular point in time. So dou u by dou x average we same as 1 by t0 0 to t0 dou u by dou x dt. So this dou by dou x term can take it outside. You could be written as integral of the derivative could be written as the derivative of the integral if the upper and the lower terms are constants. So if the upper limit and the lower limits are constant, then the derivative of that constants will be equal to 0, and therefore we can write the integral is equal to the derivative using the Leibniz theorem that we have seen in one of the previous lectures. When I discussed about the derivation of the integral equation for a flow over a flat plate, derivation of the integral momentum equation for a flow over a flat plate. 1 by t0 dou by dou x of 0 to t0 u dt. So this is basically 1 by t0. We take it outside, so it will be dou by dou x of 1 by t0 0 to t0 u dt. That will be equal to u bar divided by dou x. That completes the fifth identity. And now 26. We need to prove the derivative of this mean component will be equal to 0. That is given because it's a constant. It doesn't vary with respect to sign. That's a given. That's straightforward. Equation 7, we have to see the average of the velocity over the time will be equal to 0. Not just the mean term, but the variable term as well. Fluctuation term as well. So dou u by dou at over averaging of the dou u by dou t term. So that will be 0 to t0, 1 by t0, dou u by dou t dt. So this could be written as, once again, taking the dou by dou t term outside. So dou by dou t of 1 by t0, 0 to t0, u dt. So this will give us the dou by dou t 1 by t0, 0 to t0, u mean plus u dash dt, distributing the integrand. That will be 1 by t0 integral 0 to t0 u bar dt plus 1 by t0 integral of 0 to t0 u dash dt. So in this case, the second term is the integral of the fluctuating term that is equal to 0 that we have seen. Uh, that is a rule. So based on that, this particular term will be equal to 0. And what remains is d by dt of 1 by t0, 0 to t0, u bar dt. So just like the previous case, we will take the integral inside, just because the upper and the lower limits are constants based on the Leibniz theorem. So it will be rho by dou t of u bar dt. So in the previous case, what we have seen is that dou u bar by dou t is equal to 0. So this term will become equal to 0. So that gives a total term will be equal to 0. So that completes last identity as well. So this was the this was one exercise that we have done to check for the validity of these time averaging rules that we directly use in the case of Navier-Stokes, the deriving Reynolds average Navier-Stokes equation. So using these mathematical calculation formulations, we have obtained that these set of equations are truly valid and we can use it straight away. Look into the second problem. We need to derive the time average form of the energy equation by starting from the energy equation and applying the rules of time averaging that we have seen in the previous question. Just look into it and start it. In fact, I'll also start within a couple of minutes. The given form is not a conservative form. We have to change it from the so the given form is a total differential based form. We have to change it into the conservative form, and then we can start deriving. So this particular term can be expanded as rho Cp into d by dt, written as dou t by dou t plus u dou t by dou x plus v dou t by dou y plus w dou t by dou z equal to alpha dou square t divided by dou x square plus dou square t divided by dou y square plus dou square t divided by dou z square. So this is the conversion term, and the right hand side is the diffusion term. And this is the non-conservative form. So we try to change this equation into the conservative form by adding the continuity equation to it. So continuity equation says that dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. So we can represent it by t2, and we multiply it by t and add it to the first equation. So 2 into t plus 1 will give us rho Cp Okay, we can multiply it by rho Cp as well. Rho Cpt. So this is rho Cpt, rho Cp. So the rho Cp term will go outside. So it will be dou t by dou t plus u dou t by dou x plus t into dou e by dou x. U dou t by dou x plus t into dou e by dou x. Similarly, v dou t by dou y plus t into dou e by dou y plus w dou t by dou z plus t into dou w by dou z are equal to the right hand side. Beg pardon, this is k. There's a small correction. This is k. K dou square t divided by dou x square plus dou square t divided by dou y square plus dou square t divided by dou z square. So we can represent the left hand side in terms of the flux. That is in the conservative form, where in order to identify the conservative form, we can easily say that this will be net flux form, where the coefficients of this term will not be a variable that will be present inside the derivative. So rho Cp dou t by dou t plus dou by dou x of ut plus dou by dou y of vt plus dou by dou z of wt is equal to k dou square t divided by dou x square plus dou square t divided by dou y square plus dou square t divided by dou z square. So we have got this form. This is the conservative form, and we can denote it by equation 3. We can denote it by equation 3. Equation 3 is the conservative form of energy equation. So that is dou t by dou x plus dou ut by dou x plus dou vt divided by dou y plus dou wt divided by dou z into alpha into dou square t divided by dou x plus dou t. That could be written as del squared t. So we have this 4. We need to find the Reynolds average Navier-Stokes equation of the trials of 4. So basically what we do is we integrate and divide it by T0 of dou t by dou x plus dou by dou x of ut plus dou by dou y of vt plus dou T divided by dou z equal to right hand side will be dou by dou T of dou by sorry alpha into this closures. So it will be alpha into integral of 0 to t t0 1 by t0 alpha into del square t dt. Also dt. So in this one, we use the rules, Reynolds averaging, time averaging rules that we have seen in the previous case. The first, thereby the time average, we consider t as a variable here. So the first term will dou t by dou t, and we can find there's a small correction. So the first term will be dou t by dou t of integral 0 to t divided by t0. That is the time varying factor. So we have seen that the equation 8 shows that the average of the time varying factor will be equal to 0. So we have proved it. We have proved that this is the equation 7. Sorry, equation 7. So just replace u by t, you get the average of the unsteady term will be equal to 0. So this particular term will be straight away 0 from identity 7, and going to the second term, that is the average, the time averaging of the product, derivative of a product. So that will be quite similar to the confusion can be avoided. So I'll just open a small figure here. So then I try to derive it 0 to t dou by dou x of ut by 1 by t0 ut. It's quite similar to the thing which you have seen previously. So take the dou by dou x term outside. It's independent because 0 and t0 are constants. And then the 1 by t0, 0 to t0, ut dt. So it will be a product, so just like the UV term, just like the average of UV, it will be having two terms, U bar V bar into U dash V dash bar. So it will be dou by dou x of this could be written as U bar V bar plus U dash V dash bar. So instead of V, you can write it as T. So we have two terms. That will be dou by dou x of, we just separate it out, dou by dou x of U bar T bar plus dou by dou x of the average of the fluctuating quantities. U bar T bar, the average. This you can denote it by, there was a slight confusion, sorry for the trouble. So this will be, you can denote it by equation 5. So basically the averaging of this particular term of the of this ut term will give us the product of the average plus this particular term. So this will give us, the first term will be 0 and the second term will be dou by dou x of u bar t bar plus dou by dou x of u dash t dash bar from equation 5. So that is it for for this particular term. Similarly, for the VT, we can denote it as V bar T bar plus dou by dou x of V dash T dash bar. Similarly, for the last term, can write it as dou by dou set of omega bar t bar plus dou by dou set of omega dash t dash bar. On the right hand side, it will be straightforward. So you have this. Yeah, on the right hand side, it will be alpha delta square t. So the derivative of the integral will be same as that of the integral of derivative. So you can take it to be the average of that straight away. So it will be 1 by t0. This particular term could be written as it will go inside. So straight away, you can write it in terms of an average quantity. So it will be alpha into delta squared t. So that will be equation 6. So all these terms are from the equation 5. So we could denote it by integral of the time averaging of a derivative ut could be written as the derivative of uh, the derivative of the product of their means plus the derivative of the mean of their fluctuating terms. So every equation will be having these two terms. Every term will be distributed into these two terms, and the right hand side will be straightforward alpha delta square t. Now what we need to do is we need to split it. So what we could see is that this term could be written as u bar. It's basically this term could be split into two. So it's a basic multiplicative rule. Chain rule we can apply. So it will be u bar into dou t bar by dou x plus uh, uh, t bar into dou e by dou x. So that implies it will be t bar into dou u bar by dou x plus u bar into dou t bar by dou x plus u bar. Similarly, the other terms will also come into picture. So t bar dou v bar by dou x plus v bar dou t bar by dou x. It will be dou t bar by dou x plus for the w term as well, it will be t bar w dou bar by dou x plus sorry, this will be y uh, and uh, and this will be set w bar dou t bar by dou set. And the fluctuating terms will be there. So that will be written as dou by dou x u dash t dash bar plus dou by dou y of u v dash t dash bar plus dou by dou z of w dash t dash bar is equal to alpha delta squared t bar. This will be 7. So we have the seventh equation and we try to club a few terms together. So that will be the first term will be here it will be u bar dot t bar by dou x. We club these terms together. So it will be u bar dot t bar by dou x plus v bar dot t bar by dou y plus w bar dot t bar by dou z. And the other terms in terms of dou e by dou x, so you can club together. So it will be t bar dou u bar by dou x plus dou v bar by dou y plus dou w bar by dou z. So this is a continuity equation that will be equal to 0, unity equation, plus the fluctuating terms that will be dou by dou x of u dash t dash by average. I beg your pardon for some confusion that happened in the starting of this problem where I told that this particular term will be 0. No, it won't become equal to 0 because that particular term will remain 1. So there's slight confusion regarding the identities that we have used prior. So that will be w t bar bar. That will be equal to alpha into del squared t bar. So the left hand side will be having these terms and the right hand side will be this minus this. So basically we'll be having dou u by plus v bar. The fluctuating terms will remains in the equation, so it can't be so Rayner's average Navier-Stokes equation can't remove the fluctuating terms later. So this will be alpha. We try to expand it alpha into t bar dou square t bar. So that will be dou square t bar by dou x squared plus dou square t bar by dou y squared plus dou square t bar by dou z squared. And take the fluctuating terms, the mean of the product of the fluctuating terms on the left hand side on to the right. So it will be u bar t bar just reassembling the terms. So that is the time average form of the energy equation. We have started from the base form of the non-conservative form of the energy equation, and we applied the Reynolds average Navier-Stokes equation. We average the Reynolds averaging for this energy equation and use the identities that we have used that we have derived in the first question and arrived at the Reynolds average form of the energy equation. This is the Reynolds average energy equation. Now we can move to the third problem. Prove that in a time average turbulent boundary layer, the total flow rate through the viscous sublayer 0 to y 0 to y viscous sublayer thickness u bar dy is independent of the longitudinal position x. It's also a derivation that is based on the viscous sublayer thickness. And this requires a bit of knowledge about what is the viscous sublayer thickness and how much is the normal order of thickness. And the normal the non-dimensional wall coordinate that we use for So this is a straightforward problem, but if you know the basics of it, we can directly solve it straight away. Uh, so we need to show that the integral of 0 to the viscous sublayer thickness u bar dy is independent of the longitudinal position of x. That is the time average, basically averaging with respect to the vertical distance of the mean component of the velocity is independent of the longitudinal position with respect to x. So for that, we need to know what is u bar, and we will try to represent everything in the form of a we'll try to represent everything in the form of non-dimensional coordinates. So wall, nearby the wall coordinate, non-dimensionalization. So what we could write is that the non-dimensional value of velocity u plus can be written as the average velocity divided by uh, u star, where the u star term is a friction velocity or shear velocity that could be written as root of shear stress divided by the density. Similarly, the v plus can be written as v bar divided by u star, the same shear velocity. Then x plus could be written as the x dimension, non-dimensional x dimension, non-dimensional coordinate, wall coordinate x plus could be written as x x divided by u star divided by nu. That is a kinematic viscosity term. Similarly, y direction, y plus could be written as y into u star, the shear velocity divided by nu. These are the wall coordinate non-dimensional terms. So in the viscous sublayer, In the viscous sublayer, here the kinematic viscosity term that dominates over the eddy viscosity term due to the turbulence. So effect of the friction, the fluid friction dominates over the turbulence in this particular region nearby the wall. So that's why it's called a viscous sublayer. So in this particular problem, we have to actually do the integration till the viscous sublayer, and u bar is the mean velocity component. So we currently have got this equation. We need to do the integration basically. So you know the value of u bar. You can actually write u bar in terms of u plus and u star. Similarly, dy can also be written in terms of the non-dimensional coordinates. So integral of 0 to y VSL u bar dy is equal to, so u bar can be written as u plus into u star, u plus into u star, and dy can be written as dy plus into nu divided by u star. So integral of y VSL. So this y VSL, this limit actually changes to y VSL plus. You can write it as y VSL plus analogous to y plus and y VSL plus. So this u star gets cancelled. So it will be did I miss one term? So this will be u star get cancelled. So it and then this new can go outside. This kinematic viscosity 0 to y VSL plus u plus dy plus. So what we could see is that this particular term we have non-dimensionalized in terms of u plus value and the dy plus value. So what we could see is that within the within the viscous sublayer, for we could write for viscous sublayer, we could write the velocity profile u plus is equal to y plus. This is only valid for the viscous sublayer and not even valid for the turbulent sublayer. So in the turbulent sublayer, it will form a it will actually depend upon a log ratio. It will take a log form. So in the viscous sublayer, you could write it to be u plus is equal to the non-dimensional velocity u will be equal to the non-dimensional y coordinate. So straight away we can substitute that. Therefore, integral of 0 to y VSL y VSL u bar dy equal to y plus in the will be equal to mu into 0 to y VSL plus y plus dy plus. So it will be mu y plus u, so y plus squared by 2 0 to y VSL plus. So it will be mu y VSL plus the whole square divided by 2. So this particular term, this y VSL is the viscous sublayer thickness, in the non-dimensional form. So this particular term is a constant for the viscous sublayer throughout. Though the actual thickness of the viscous sublayer will vary, this is a non-dimensional coordinate that is based on a similarity variable that we have used. So this particular term YVSL is actually dependent upon Y U star and U star by nu. So though the Y value vary with respect to the viscous sublayer, the YVSL plus will not vary. So here YVSL U star, and we are trying to non-dimensionalize it with respect to the U star velocity. This takes the shear stress divided by rho and nu. So this particular term, shear stress, will vary with respect to the surface, and we are trying to non-dimensionalize it. So this term is a constant for viscous sublayer. And this viscous sublayer, we could see that it takes of the order of this YVSL is plus is of the order of is 10, is of the order of 10. So that's why we could say that this particular integral is independent of x. So in this case, when we integrate it with respect to VSL, there is no term that shows that this is dependent upon, though the y will vary with respect to x, y VSL plus will not vary. And therefore, we can say that this integral is a constant. Looking at the fourth problem, this is also a derivation for the skin friction coefficient formula recommended by Prandtl's 1/7 power law velocity profile. So the velocity profile takes the u by u takes the 1/7 power law form, and can write that u plus is equal to u plus. We have seen in the lecture, we have seen in the previous question as well as in the lectures, u plus is equal to u bar by u star. So we have a relationship between u plus and the y plus. The in the previous case for the viscous supply, we have seen that u plus is equal to u plus is equal to y plus straight away. But for the turbulent layers, that's for the viscous sublayer. In the previous case, we have seen it for the viscous sublayer. But for the turbulent layer, this velocity profile is not valid. We have to go for some other alternative velocity profile. So based on a fit, we know that u plus will be a function of y plus. Similarly, u infinity plus will also be a function of y plus. So we could see that for the velocity profile, which takes a power of 7, we can write it specifically straight away. Look into the problem, and I'll also try to solve it in a couple of minutes. So in this particular problem, it's been mentioned we have to find the skin friction coefficient formula by Prandtl's 1/7 power low velocity profile. So first of all, we need to know what is the velocity profile that we will be using in this case, and then we'll try to solve it. So first of all, we need to know the velocity profiles. So this is one. In the previous case, in the viscous sublayer, we could have straight away taken u plus is equal to y plus. But here it is not that case. It is 1/7 the law. So we could write u plus is equal to a coefficient c into y plus the whole power 1/7. So u plus is the non-dimensional wall coordinate for u. Similarly, y plus is the non-dimensional wall coordinate for y. Since coefficient c is something that we require. So based on a fit, we can take it in the lecture also we have seen it. We can take this fit to be 8.7. So that gives u plus equal to 8.7 y plus the whole power 1/7. Similarly, u infinity plus could be written as 8.7 into y. Instead of y, it will be delta. The u infinity will be present at a distance delta away from the wall. That is a boundary layer thickness 1/7. So that also we have to non-dimensional this. So u plus is nothing but u. As we have seen in the previous case, u plus is equal to u bar divided by u star. U plus is equal to u star u bar divided by u star y u infinity plus is equal to u infinity divided by u star y plus is equal to y u star divided by nu, and then delta plus is equal to delta u star divided by nu. So dividing 1/2, we'll get a ratio u plus could be written as u bar by u star. So u bar divided by, similarly, u infinity plus could be written as u infinity by u star. So that gives a left hand side, right hand side. Similarly, we could write it as y by delta the whole power 1. So this is the velocity profile of Prandtl 1/7 velocity profile that relates u plus with the y plus the whole power 1/7, and this coefficient we have to take for solving for the analysis. This is something it's based on the coefficient of fit that is experimentally determined. So we should know what is a fit for this case. So that will be u bar by u infinity is equal to y by delta the whole power 1/7, that is 3. So this is a velocity profile, and now we can substitute this in the momentum integral equation. So just like the previous force conversion case and free for the laminar flow, we have to use the momentum integral equation. So the base equation without the pressure gradient terms. So that form will be dou by dou. So delta u bar u infinity u bar instead of u, it's a turbulent flow. That's why you are writing it as u bar. There in the laminar flow, everything was u itself straight away. So dy equal to shear stress divided by. So we need to substitute this u bar based on the velocity profile. So sub 3 in 4. We can write everything in the form of this equation. So we can just take the u infinity term outside. So we can write d by dx. So u infinity squared 0 to delta u bar by u infinity 1 minus u bar divided by u infinity dy equal to rho divided by rho. So basically, you need this formula that is equal to y by delta the whole power 1/7. So d by dx u infinity squared 0 to delta y by delta the whole power 1/7 into 1 minus y by delta the whole power 1 by 7 dy equal to tau rho divided by density. So we can directly integrate it. So this varies from 0 to delta, and y is the dimensional dimension for the integration. So that particular integration gives us the value constant integral value equal to 7 by 72. Then substituting that value back, we get the dou by x u infinity square delta into 7 by 7 by 2. So equal to tau rho divided by shear stress divided by density. So we have got it straight away. Now the left hand side you can write it as, so since this is a flat plate case, we can write this this u infinity will be constant, and you can take the u infinity outside. So the only term that remains is delta, that is within the boundary, within the derivative 72 by 7 tau rho by u infinity squared rho. So this is one relation between the delta and the shear stress. Then you need another relationship to find the value of shear stress. And when we substitute that, if we can get the value of the shear stress in terms of delta, then we can substitute and calculate the value of the delta straight away. And once you get the value of delta, you can back substitute to get the value of shear stress. Either way, you can calculate it. So in order to find the value of shear stress or delta, you need to represent the other term in terms of the term which you require. So this is one equation, one relation between shear stress and the delta. In order to solve, we need another equation as well that we can get from the base equation. So unlike the previous case where we could have directly written shear stress is equal to dou u by dou y at the world, it's not possible here. Instead of that, we can use the definition straight away. So definition of the u infinity plus is nothing but u infinity divided by shear stress divided by dou. There is a shear stress term, and we know a relationship directly since a power law relationship we are using straight away. We can use it here as well. 8.7. This will be delta plus whole power 1 by 7. So this delta plus we can denote it as delta shear stress divided by rho, the whole raised to 1 by 2 divided by mu, the whole power 1 by 7. So this is basically a relationship, another relationship that straight away gives. This is actually another relationship between shear stress and the delta value. So from this we can assemble a few terms and combine and write it as so combining and as assembling a few terms, we can write shear stress divided by rho is equal to u infinity raised to 7 by 4 mu raised to 1 by 4 divided by 2.7. That's a constant raised to 7 by 4 delta raised to 1 by 4. So this is another relationship between shear stress and the delta. In the previous term also we had a shear stress and delta term. Now we just substitute this shear stress by rho in the previous equation. We can get the everything in terms of delta. So it will be delta raised to 1 by 4 d delta by dx sub 6 in 5. We can get shear delta raised to 1 by 4 d delta by dx is equal to mu by u infinity raised to 1 by 4 72 by 7, 8.7 raised to 1 by 4. Now we integrate from integrate with respect to x, this one, for delta equal to 0 at x equal to 0. That will be the boundary condition. We can actually get the value of the delta, and from the delta we can back substitute to get the value of the shear stress. Because in the equation 5 we have a relationship between straight away between the shear stress and the d delta by dx. So this can be written as, so this could be written as, so d raised to 5 by 4 divided by dx could be written as will be d raised to 5 by 4 d raised to d raised to 1 by 4 d delta divided by dx. So therefore, this particular term would be written as delta raised to 1 by 4 d delta by dx is equal to 4 by 5 d delta. So delta raised to 1 by 4, this term can be written as 4 by 5 into d delta raised to 5 by 4 by dx. So back substituting that, so this will become 4 by 5 d delta raised to 5 by 4 by dx is equal to nu by u infinity the whole power 1 by 4, 72 by 7, 8.7 the whole power. This will be whole power half 1 by 4. Beg your pardon, sir. That's 7 by 4 actually. So in this case, we integrate and take the 4 by 5 on the other side. We get d delta raised to 5 by 4 by dx equal to nu by u infinity raised to 1 by 4, 72 by 7 into 5 by 4, 8.7 raised to 7 by 5. So integrating it with respect to x, and for the condition of at x equal to 0, delta equal to 0, we'll get this will be delta raised to 5 by 4, and this whole term multiplied by x plus constant is equal to 0 for this case. So taking the x on this side, you'll get nu by u infinity raised to 1 by 4, 72 by 7 and the other constants. This particular term will be 72 by 7. It's 18 into 5, 90 by 7. By 7 into 8.7, the whole power 7 by 4. And we can actually do some kind of manipulation. So we multiply both the side by 1 by 4. It will be x raised to 1 by 4, and then this x goes inside. So it will be delta by x raised to 5 by 4. So we can denote it as delta by x is equal to mu by u infinity by x raised to 1 by 4, 90 by 7, 8.7, the whole power 7 power 4, the whole raised to 4 by 5. So that will give us the value of delta by x. Delta by x is equal to a constant multiplied by nu by u infinity raised to 1 by 5. So the constant is equal to 0.373. So this particular constant will become equal to 0.373 multiplied by nu by u infinity x raised to 1 by 5. Can denote it by 7. So we know the value of delta by x. Now what remains is we need to substitute it back. So we have a relationship between tau rho by rho in terms of equation 5, tau rho by rho in terms of delta d by dx. Now we know delta is equal to some constant into x. So d delta by dx will be equal to this constant 0.373 into nu by u infinity nu by u infinity x raised to 1 by 5. So d delta by dx is equal to the same term. So taking the derivative of delta by x, we'll get it's not required actually. We can directly take a delta by x is equal to 0.373 mu divided by u infinity x raised to 1 by 5. Substituting delta in equation 6, we'll get rho 0 divided by rho infinity squared equal to 8.7 raised to minus 7 by minus 7 raised to 1 by 4. We have taken the u infinity squared here, so there is a u infinity raised to 1 by 4 that remains in the denominator. So we can club them together with the nu by u infinity term. It will be nu by u infinity, nu raised to 1 by 4, u raised to 1 by 4, nu raised to 1 by 4, u raised to 1 by 4, 8.7 raised to minus 7 by 4, and delta raised to 1 by 4. That will be so it will be equal to 8.7 raised to minus 7 1 by 4 into uh, nu by u infinity delta raised to 1 by 4. So this is just clubbing the few terms together. We can substitute the value of delta in terms of x, and we can write tau 0 divided by rho infinity squared as a function of u infinity delta divided by nu. So we'll get we can back substitute everything. So it will be tau 0 divided by rho infinity squared. We have to find in terms of skin friction coefficient. So that will be 8.7 raised to minus 7 1 by minus 7 raised to. So that will be so that will be equal to 8.7 raised to minus 7 by 4. That will be 0.00227 u infinity by delta divided by nu raised to minus 1 by 4. So that almost also just substitute just like the delta. So it will be rho 0 divided by rho infinity squared is equal to 0.0227. In terms of delta, we'll get just substitute the value of delta. That will be equal to u infinity divided by nu raised to minus 1 by 4 will be equal to 0.373 nu divided by u infinity x. That will be this will be raised to 1 by 5 raised to minus 1 by 4. So we calculate the value of delta, and this delta will go on the top and raised to minus 1 by 4. So this will be the final value of the skin friction coefficient. So if you have to represent it in terms of the pure form, that will be tau 0 divided by half. You have to divide this both the left side and the right side by half. So it will be half rho u infinity squared. So this will be half. So basically, we have to multiply this quantity by 2 to get the actual value of the uh, skin friction coefficient in terms of uh, the normal nomenclature. So it will be 0.0454 u infinity divided by mu raised to minus 1 by 4 into 0.373 mu b u infinity raised to 1 by 4 x raised to minus 1 by 4. So that gives the skin friction coefficient for this particular case. For the power law, when we are using the Prandtl's 1 by 7 per power law velocity profile. Look into the last problem for this session. It's you have to derive the formula for the L average Nusselt number, assuming that laminar turbulent transition is located at a point x between x and x equal to 0 and x equal to L, where x u infinity by mu is equal to 3.5 into 10 power 5. That is basically the transition Reynolds number is considered to be 3.5 into 10 power 5 in this case. Consider heat transfer in boundary layer flow for an isothermal wall. It's a flat plate T0 to a constant temperature stream U infinity T infinity. The leading laminar section of the boundary layer has a length comparable with the length of the trailing turbulent section. So both the lengths are almost identical. We need to consider the heat flux average over the entire length L influenced by both the sections. So basically it will be the first section will be laminar and then it will go to the turbulent case. So it's laminar and X turbulent. It's laminar. So the L average Nusselt number will be equal to can be given as a total heat transfer coefficient, a total heat flux divided by delta T into the L divided by K. Basically HLC divided by K. Characteristic length for a flat plate will be equal to the total length of the plate. So the total heat transfer is equal to 1 by L 0 to X transition, that is the X lambda case. So this can actually be written in a different manner. So So this could be written as 1 by L 0 to XL Q laminar dx plus XL to ideal. It should not be L minus XL. It should be L actually. So this should be 0. It can be written as XL, subtracting everything by XL, it will be 0 to L will become L minus XL will become equal to XT Q double dash turbulent dx. So this can solve half of our problems by doing this transformation. Then for the laminar side, it's equal to the normal heat flux Nusselt-Number correlation. We can use 0.332 Prandtl number raised to 1 by 3 constant for isothermal wall, Reynolds number raised to 1 by 2 K delta T divided by X. Similarly, for the turbulent section, we have to use a correlation. Skin friction coefficient as well as the heat transfer. So using the standard number. So standard number could be written as Prandtl number raised to minus 2 by 3 half of CFX. So this for the turbulent flow, this particular term is equal to 0.0296 Reynolds number raised to minus 1 by 5. So we can write it as so when we integrate from 0 to L Q turbulent, we can write it as 0.037 rho Cp U infinity delta T Prandtl number raised to minus 2 by 3 Q infinity by nu raised to minus 1 by 5 into this will be written as this X turbulent. So X turbulent raised to 4 by 5. So we know the value of Q laminar and turbulent, substituting the average value. Therefore, the Q 00L, the heat flux over the length L will be equal to 1 by L of the sum of these two terms. Prandtl number is 1 by 3. Prandtl number, this is XL Excel K delta T plus 0.037 rho CP U infinity delta T final number is to minus 2 by 3 U infinity divided by nu minus 1 by 5 x turbulent raised to 4 by 5. So that gives the heat flux the which is averaged over the entire length. So basically we have just added the laminar heat flux as well as the turbulent fluxes and divided by the length to get the average heat flux. That completes the problem set for this week. In this week, we have seen a few derivations based on the turbulence Rand's equation, boundary layer heat transfer, and energy equation. How to derive Reynolds average energy equation. That was one question that and that used these identities for the time averaging rules. And then we have seen scaling analysis. That's all. Thank you.